Hello everybody and welcome to our 6.3 concept video, and this is actually the last set of videos for this class. This is as far as we go, 6.3. But this section is talking about optimization of multivariable functions. How do we optimize these functions that have multiple independent variables? Well, to help us really understand this, I want to start by showing you what a multivariable function actually looks like. So this is a 3D model of a multivariable function. We can see that over at the top left. There's my multivariable function in terms of both x and y. And you'll notice the difference between a normal, just single variable function. With a single variable function, we have a two-dimensional graph where we have a line on that graph that we can, depending on the function, can change what shape that line is in. It could be straight if it's linear, it can be curved, it can be a parabola, it can be a circle, right? We can change the shape of that line. When I'm working with a multivariable function, it changes everything to 3 dimensions. And so I have this 3D model that the function is represented by this surface. Instead of having like a line or like a piece of string that I can mess around with, a multivariable function is like you having a piece of paper that you can mess around with and change the shape of. 3-dimensionals, we end up having this surface that we're looking at. Well, where does optimization come into this? Well, even though I now have a surface that I'm working with, you'll notice with this shape that I still have a local minimum. I still have a point on this surface that's the lowest point in the general area. So with multivariable functions, you can still have local minimums and local maximums. And based off of what we learned back in chapter 2, how do I find these local minimums and local maxes? I use derivatives. So let's go back and see how I can actually use derivatives to do this. So the fact that we can use derivatives to find local mins or local maxes, that's not anything new. That we learned that in chapter 2. But how does this work if I have partial derivatives, right? I've got multiple independent variables. So how does this same process work if I have a derivative in terms of x and a derivative in terms of y? Well, let's remember how it worked earlier. What was my process back in chapter 2? If I had some function of x, I would take the derivative of the function, set it equal to 0, and solve for that value. If I ended up getting a value a, such that the derivative at that point was equal to 0, we called that a critical point. Why is this considered a critical point? Because if my function has a local max or a local minimum, it has to happen at a critical point. Well, the process is very similar with multivariable functions. If I have a multivariable function, then I can take the derivative in 2 different ways. I can take the partial derivative in terms of x and the partial derivative in terms of y. And what I'm going to look for is I'm going to look for critical points. Critical points where both of these partial derivatives are equal to 0. So I can set both of these partial derivatives equal to 0 and solve them. And if I come up with a critical point, or if I come up with a point a, b, notice it's a combination of both an x and a y value because they're 2 independent variables. If I come up with a combination of, or a coordinate a, b, such that the partial derivative in terms of x is equal to 0 at that point, and the partial derivative in terms of y at that point is equal to 0, then AB is a critical point. So that's the first step to this process, is first I have to figure out where the minimums and maximums could possibly happen, right? I have to find the critical points. And so in this case, with multivariable functions, it's as simple as finding both partial derivatives and setting them both equal to 0. But where do we go from there? If you remember back in chapter 2, we then had to use either the first derivative test or the second derivative test. Well, the first derivative test gets pretty complicated once you're working with multiple variables. So instead, we're going to do something similar to the second derivative test. In fact, it's called the second derivative test for multivariable functions. Specifically 2 variable functions, as in I have 2 independent variables. Well, if it's the second derivative test, I'm going to have to find second derivatives. And so the way this works is we have a certain equation that we can solve for. We label it D for determinant. It's going to determine whether it's a minimum or a maximum. And the way this determinant works is you find your double derivative in terms of x, and you plug in the critical point. If we're on to this second derivative test, we should already have my critical points by this point. So I'm going to find my double derivative and plug in that critical point. But because it doesn't just depend on one variable, I also have to do this with the double derivative in terms of y. And I'm actually going to multiply those two together. And then I'm going to subtract the mixed derivative of xy with that critical point plugged in. And then I'm going to square that value. So this is my determinant. I take these three different second order derivatives. Notice this specifies my second derivative in terms of x and then y. Does it matter if I do the y first and then the x? No, remember with that mixed partial derivative, that mixed second order derivative, it doesn't matter what order you go in. So when I do this calculation, there's actually four different possibilities that could happen. And remember, that's how it worked with the second derivative test before in chapter 2 is you calculate the second derivative at the critical point, and then based off your result, there's three different possibilities. The same thing is true here. So my four possibilities are, 1, if your determinant, this value that you just calculated, is greater than 0, and your double partial in terms of x is greater than 0. Well, what does that mean? Well, if your second derivative is greater than 0, that means your function is concave up. Therefore, we're looking at a local minimum at this coordinate point AB. Now, I specifically used the double derivative in terms of x, but it turns out this also works if you do the double derivative in terms of y. So the same thing is true if you switch to the double derivative in terms of y. Okay. Option 2, if your determinant is positive, if your calculation is positive, and the double derivative in terms of x or y, remember it doesn't matter which one, at your critical point is negative, then I have a local maximum. Now this is interesting because I now have both options of local min or local max, but I haven't even talked about, well, what happens if your determinant is negative? Well, it turns out that if your determinant is negative, then your function has what's called a saddle point at your critical point. What is a saddle point? Well, let's look at this. Let's go look at my example picture. So here's my three-dimensional function, and I have this local minimum where the function dips down and then goes back up. But it turns out if you were to do this process, you would also find a critical point at 0, 0. This function also has a critical point at 0, 0. And if I actually show 0, 0 on this graph, well, I'll do it one at a time. So if I look along the x-axis, or I guess this is actually along the y-axis. If I look along the y-axis, you'll notice why it has a derivative of 0 at 0, 0, right? That graph is flattening out, kind of like an x cubed function. It's flattening out at the origin, 0, 0. I could look at it with the y value as well. I could look along the x-axis and I see the same thing. It's flattening out at 0, 0. So my partial derivatives are both equal to 0 at that point. But if I look closely at what's actually happening, let me zoom in, I have a shape like this, which of course is not a local minimum or a local maximum. It's not the highest point in the general area, and it's not the lowest point in the general area. Instead, it creates this kind of saddle shape. You could think about sitting down in this spot, right? Like you're on a saddle of a horse. That's why it's called a saddle point. So it still pops up as a critical point, but it's not a local min or a local max. So if you do this calculation and your determinant ends up being less than 0 or negative, then your function has a saddle point at that critical point. The last option, what happens if your determinant is equal to 0? Then I can't make a conclusion, and I'm stuck. And honestly, we don't have any other options. We're not going to go into any other options in this class. So if you end up with a determinant of 0, you're just stuck. There's nothing else you can do. And you just say, I can't make a conclusion. It might be a local minimum, local maximum. It might be a saddle point. I just don't know. I would have to maybe use a graph to figure it out. Okay, but that's the second derivative test. That's how I actually decide if these critical point coordinates are actually minimums or maximums. Okay, go ahead and give this a try on the homework. See if you can figure out where these multivariable functions have minimums or maximums. If you get stuck, go check out the examples video. Good luck.